Okay, so we started with arithmetic sequence, which we understood to be an ordered list of numbers. For arithmetic, there was a common difference, and what you saw was that it looks like you keep adding the same number to get to the next term. We moved on to arithmetic series. We learned that the series is the sum of the sequence. And we learned how to add up to evaluate a finite sum, which is all that's possible with arithmetic series. And next we move on to geometric sequence. So we're going back to sequences, but we're introducing a new kind of sequence. This is the one that it looks like you keep multiplying by the same number to get to the next term. We've actually seen this pattern a few times, but we didn't call it anything yet. And so this lesson, I'm calling it geometric sequences, but we're actually going to get into the first part of geometric series, because that actually splits into two different parts, and I think it's better we just cover these two parts today. In the end, you can see it's a relatively short lesson. It's got 19 slides. And then we'll save the last little bit for the next day, because we'll actually have a quiz that day too, so that'll give us more time. So again, what it looks like when you have a geometric sequence is it looks like you keep multiplying by the same number. We've seen this before. We've seen things like 1, 2, 4, 8, 16. That's geometric, right? This time it's not a common difference. It's called a common ratio, right? Ratio is the lowercase letter r. So in this case here it would be 2. The r equals 2 because that's what you keep multiplying by to get to the next term. The thing you want to keep in mind here is that, let's say you have 1 1/2, 1/4, 1/8, 1/16. In your mind, you may still think you're dealing with a 2, but actually you're dividing by 2, which means you're multiplying by 1/2. So when these numbers are getting smaller, then the r is less than 1. It's a fraction. So don't try to call something like this r equals 2. If r equals 2, the numbers should look like they're getting bigger. Okay, so here's our two formulas for how do we find the nth term of a geometric sequence in a recursive way, meaning by defining it based on the term before, or an explicit way, meaning just if you plug in the n, you're going to find out what that term in the sequence is. So let's see. Let's go on to the next slide. So remember that explicit formulas for the nth term of the arithmetic sequence are going to be linear. That's something we've actually already covered. For geometric, the formula for the nth term of the sequence, it looks like it's exponential. You know, something that looks like 2 times 3 to the n. That looks kind of exponential. And that's what we expect to see from a geometric sequence. So, is this sequence geometric? If so, what are the a1 and the r? So again, in your mind, you might be thinking just, does it look like I keep multiplying by the same number? And you're going to say yes. By the definition, the common ratio means you're going to divide 6 divided by 3, which is 2. 12 divided by 6, which is 2. 24 divided by 12, 2. 48 divided by 24, 2. They all equal 2. Therefore, it's geometric, and r equals 2. And they actually asked for the a1 Remember, A1 just means the first term, that is 3. Same deal. Is it geometric? If it is, what is the R? What is the A1? Okay. Again, you're going to look at this right away and say, I see a pattern. Okay, but is it the right pattern to call it geometric? If I divide 6 divided by 3 is 2. 9 divided by 6 is 3 halves. Since those two are not equal, this is not geometric. Does it have a pattern? And yeah, it does have a pattern. It's arithmetic. It looks like you keep adding 3 to get to the next term. So it has a common difference, but not a common ratio. Right? Is this sequence geometric? Okay. Again, if we do the 3 to the 10th over 3 to the 5th, remember, properties of exponents says we should subtract the exponents. 10 minus 5 makes 3 to the 5th. 3 to the 15th divided by 3 to the 10th is 3 to the 5th. Same property. 3 to the 20th divided by 3 to the 15th is 3 to the 5th. And these are all equal. So, yes, it's geometric. And R equals 3 to the 5th. And A1 equals 3 to the 5th. Okay, so try to do the first one. Let me see what I've got on here. So I've got that as 3 different slides, but in the end, we're just going to do them all. You try. So hit pause when you're done. Hit play. Let's see. Does it look like you keep multiplying by the same number? Yes. So yes, this is geometric. R equals 2. Does this one look like you keep multiplying by the same number to get to the next term? No, it looks like you keep adding the same number to get to the next term. So you're going to say no. How about this one? Okay, remember the pattern. We saw this with that previous example of 3 to the 10th over 3 to the 5th. In the end, this 2 to the 7th over 2 to the 3rd will be 2 to the 4th. 2 to the 11th over 2 to the 7th will be 2 to the 4th. And 2 to the 15th over 2 to the 11th is 2 to the 4th. So notice that the exponents, if the exponents have an arithmetic pattern, then the sequence has a geometric pattern. And this is going to be a yes. R equals 2 to the 4th. Don't like that 4. Okay. Now, the formula to find the nth term of a geometric sequence from the slide, the definition slide a few slides ago, was this: an equals a1 times r to the n minus 1. So the two things that we need to plug in are a1 and r. So let's see, a1 is 4. R, what number does it look like you keep multiplying by to get to the next term? Right? 12 over 4 equals 3. So an equals 4 times 3 to the n minus 1. That's the formula. Okay, now use that formula to find the 10th term. A10 equals 4 times 3 to the 10 minus 1 equals 4 times 3 to the 9th. And the thing about geometric sequences is that the numbers are going to get quite large quite quickly. You know, if your n is too big, it's going to really become a huge number. So just pause a second here. So I paused just so I could have Desmos open on the other screen. Didn't know what else I was going to be alt-tabbing over to. 4 times 3 to the 9th. In Desmos, 4 times 3 raised to the 9th. 78,732. And just to be clear, I think we've had this come up with exponentials. I mean, this is a situation that could have happened with exponential functions when we studied them. I don't remember it happening, but sometimes students will try to take that 4 times 3 and say that, oh, that means it's 12 to the 9th, okay? But that is not true, right? You cannot multiply the 4 times 3 because 4 is not being raised to the 9th. So don't try to ever multiply those two together and make it into one number. So try to find the 8th term of this geometric sequence. Hit pause. When you're done, hit play. So an equals a1 times r to the n minus 1. What does it look like we keep multiplying by? How about 4? So r equals 4. So our formula will be an equals a1 3 times 4 to the n minus 1. Right? That's the formula. So a8 will be 3 times 4 to the 8 minus 1, which is 3 times 4 to the 7th. Which again, I am going to do in Desmos. $49,152. Now, I believe that's probably it for sequences. So now we get to arithmetic or geometric series. Remember that a series is the sum of the sequence. And unlike arithmetic, where I showed the first slide I showed with arithmetic series was that there's finite and there's infinite. And we can't do much with the infinite arithmetic series. But we actually can do something, and it's actually quite important what we can do with an infinite geometric series. And that's the part we're saving for next class. This is a formula for how do you add up a finite geometric series. So some of the terms, most of it's familiar. You know, we use this Sn. The capital S stands for sum. Right? The R we know is the common ratio, right? The N is the number of terms, and the A1 is the first term. I mean, they're all things that are familiar. This one, even more than the arithmetic, you know, I think you end up having to go to you'll have to go to a calculator or Desmos to do most of the math. But the substituting in, we should understand how the formula works, for sure. So what is the sum of this finite geometric series? Okay, so let's see, our formula is this. Sn equals a1 times 1 minus r to the n divided by 1 minus r. Okay, let's see the things that we know from looking at this. Well, we know what the first term is. We know what the r is. And we don't know the number of terms. Okay, like we did with geometric, if you want to know, we could see what the last term is. So it's really just a matter, we can use the formula for the nth term, right? an equals a1 times r to the n minus 1. In this case, an equals 3 times 2 raised to the n minus 1. All right, we can set 3072 equal to 3 times 2 to the n minus 1. And then you solve for n. Okay, divide by 3, 1024 equals 3, or equals 2 to the n minus 1. Even that's kind of a hard calculation, to tell you the truth. I mean, you just have to know what power of 2 equals 1024. 1024 is, let's see, 64 is 6. So then we've got 128, 256, 512, and 1024. So that was 6, 7, 8, 9, 10. That's actually 2 to the 10th. And if that's, if 2 to the 10th equals 2 to the n minus 1, then 10 equals n minus 1. N equals 11. So using all of that, let's plug in. S11 equals A1, 3 times 1 minus 2 to the 11th divided by 1 minus 2. And at that point, you should go to Desmos. So let's see, 3 times let's make sure I got that right. 3 times 1 minus 2 to the 11th over 1 minus 2. That's correct. 6,141. Okay. I'm just going to say that, this whole calculation here, really makes this into something. It's hard enough to do this stuff. It's also hard to do this stuff here. And you can use Desmos in a clever way. I'm not even 100% sure where this is going to go, but we're starting with 3, and then we're multiplying times 2 on every step, right? 3. How about this? We're going to go 3 times 2 raised to the n. Okay? And yeah, not happy with that. What if I say n equals 2? So you see how I can just play around with that? If I put in the 3 times 2 to the n, I can say 2, that didn't work. 3, oops. That didn't work. How about guess 7? That didn't work. How about 9? That didn't work. We're looking for 3,024. So we try 10. Actually, what was that again? 3 times 2 at the end. 3,072. So that's where we got it right there. When n equals 10, so, actually that was wrong though. Sorry about that. It should have been n minus 1. So actually 10 would not have quite done it, but 11 does. So I mean, it might be easier just to guess and check on these, finding the right n, than it is to try to solve it like an equation. You still have to come up with this part right here. But, okay. So let's try this one. What is the sum of the finite geometric series? Okay, let's see. We're going to solve it using the formula Sn equals A1 times 1 minus r to the n over 1 minus r. The A1 is what you get when you plug in the first number. What do you get if you plug in a 0? Well, anything to the 0 is 1, so this thing just equals 4. The r is whatever is being raised to the power, 1/2, right? R is this thing right there, always. And the n, what is n in this case? It's not 20, right? You're looking at that like, if it started at 1 here, you would say that the top number is the number of terms, but they actually started it at 0, so that's 21. And so this is going to be S21 equals A1, 1 minus 1/2 raised to the 21st divided by 1 minus 1/2. And you know, you're probably not going to find it there's no reason why you don't just like plug those numbers in. And I might even agree with that now. With the calculator, it was definitely a thing where I'd want to store values. But in this one here, let's just try it. So this thing is going to be, the first term was 4 times 1 minus 1/2 raised to the 21, 1 minus 1/2. And you can see that it's 7.9999, so eventually that's just going to be an 8. This is probably Desmos not rounding off when it should have. But in order for us to know that, we would have to like go through all the math here, which I don't think we really want to do. I think that would probably be a real hard slog. So we're just going to round this thing to 8. In fact, I want to confuse things. Okay. So try to do this one in the same way. And this one, at least you know how many terms. In fact, it's so few terms, you could just like put it in the calculator and add them up. But try to use the formula to find the sum. Okay, let's see. Sn equals A1 times 1 minus r raised to the n over 1 minus r. I always start with the formula. Looks like our A1 is negative 15. The r, what does it look like you're multiplying by to get to the next term? Looks like negative 2. And the number of terms, well, we can count them. There's 6. So S6 equals negative 15 times 1 minus negative 2 raised to the 6th divided by 1 minus negative 2. And you know, this is where you definitely want to be careful about the way you put this into any kind of calculator. I know that a fair portion of you are going to try to say these minuses cancel, but they don't cancel. Because negative 2 to the 6th is a positive number. So actually there is no negative to cancel this with. That needs to stay a minus. If that had been an odd exponent, then they would have canceled. So you'd have to be more careful. It's easy. The easiest thing is just make sure you put this thing in parentheses. So let's put that into our machine. Let's see if I can do this. And the answer is 315. Okay, so try this one again. In the summation notation form, the sigma. Hit pause. When you're done, hit play. So again, if I plug in a 1 here, I get -2 to the 0, which is 1, times 5, which is 5. R is whatever is being raised to the power, right? That's why every time you increase n by 1, you get another multiplication by -2. That's what the common ratio does. And it looks like the number of terms is given to us because it starts at 1, it ends at 10. That would be 10. So S10 equals A1, 1 minus -2 raised to the 10th divided by 1 minus -2. Go to the Desmos. And I think that's it. Let's see. 5 times 1 minus -2 to the 10th over 1 minus -2. That is correct. So -1705. And at that point you say, well, can I just put this in Desmos? And the answer is yes, sometimes, some problems, you can do that. But rest assured, there will be some kind of questions on the test where you actually have to know how to take something like this and find the first term or the number of terms or something like that. Right? So don't get too lazy that everything can just go into Desmos. But this, again, where in Desmos do you find that? You go, well, you can just do this, right? You could type SUM, done. Just make sure that whatever you put in your formula, you put in parentheses, because it'll change the answer. What did we just say that was? 5 times -2 to the n minus 1. So in parentheses, 5 times -2 raised to the, and it might help to use parentheses in the exponent, n minus 1. And we get the same answer. Either way, we get the same answer. And that is, at least, it's geometric sequence. It's the first part of geometric series. That's why there'll be 2 pages of homework. And next class we'll finish with the most important part, which is infinite geometric series. That's the homework.